Now in this chapter, we've gone through the work of creating these three equations of motion for constant acceleration, and we've gone through a few examples of looking at the acceleration velocity of a car or a motorcycle. The exciting thing about this is we can look at what happens to things that are falling or that are being thrown in a gravitational field, so at the surface of the Earth. It's common that when we do this, that we talk about the vertical direction as corresponding to the y-axis. So when we're doing horizontal motion for cars, motorcycles, people walking, use the x-axis. Vertical axis, we're going to use the y-axis. And so what we do in that case is we take these original equations of motion and we just replace every x with a y. And we get these three equations that are shown at the bottom of this page. And they have the exact same form as the ones above, just where I had v sub x, I have v sub y. Where I had y, or I'm sorry, where I had x, I now write a y, etc. Now, we talked about the fact that if you hold an object in your hand and then you release it, it's going to fall towards the Earth. If we say that upwards is the positive y direction when we define this axis, what we have is an acceleration in the y direction, downwards in the negative direction, and we know the magnitude of that acceleration. It's just g equals 9.8 meters per second squared. So these three equations I have here in terms of y are going to turn into these three equations given in the middle of the page here. Notice everywhere that I had an a sub y, I replaced that with negative g. So once again, I've decided that the upwards direction is the positive direction, the positive y-axis, and the y-axis is in the positive direction, and that my acceleration is downwards in the negative direction, which is why I write a sub y equals minus g. It's strange, but every time I write the value for g down, I give it a positive value. It's a little bit counterintuitive because that's always downwards. In each one of these equations, where I had y equals y sub naught plus v sub naught sub yt plus a sub y t squared over 2, I replaced a sub y with a minus g. And you can go through for each one of those previous expressions for the equations with constant acceleration in terms of y, go through each one of them, replace a sub y with minus g, and you get these three equations. So the reason I was saying that these are useful, that they're so interesting, is they can tell us things like if I drop an object from a high place or I drop a rock down a well, what's the velocity when that thing reaches the ground or reaches the bottom of the well? Or how long does it take an object to travel when it's been dropped? And so we'll look at our first example. I just had a handwritten diagram and I was too lazy to try and redo it in PowerPoint. So you'll see my diagram here of a tower right here. It's got a height h. There's a person at the top of it, my little stick figure holding out a ball that they're going to drop or an object. And right here I'm trying to point out in this little segment that upwards is the positive y direction. And I say that h is 79.5 meters, so it's like over 200 foot. I don't know how to do the conversion, but it's going to be big. It's going to be something like 240 feet tall. If I drop a ball from the top of it and the ball is initially at rest, how fast will it be going when it hits the ground, or what will its velocity be in this case? Well, notice I know the height of this thing, I know the initial velocity, I know the acceleration. I choose this third equation that has no time in it as the equation that I'm going to use to solve this problem. So I'm going to say that drop the ball from the top of the tower, it's initially at rest, so v sub naught sub y is 0. G is 9.8 meters per second squared. In this equation I have a delta y. Notice that delta y is the change in the y coordinate. And in this case, that's going to be a negative number. I wrote equals h. That's not entirely correct here. It's actually going to be minus h. But notice I say y equals 0, y being that final height that the ball reaches, and that's going to be when the ball hits the ground here. Notice that that's where y equals 0. It begins y sub naught at 79.5 meters up in the air. So delta y is y, which is 0, minus 79.5 meters, or minus 79.5 meters. Anywho, taking that negative value of y, I'm going to plug that into that expression. Notice I'm trying to solve for v sub y. So I take this expression, I take the square root of each side, and that gives me this expression which we'd seen before. Inside the radical, under the square root symbol, I have v sub naught sub y squared minus 2 times g times delta y. Delta y is going to be a negative number, so these two negatives are going to cancel out. It's worth getting your calculator out, plugging these numbers in, and running it through, and you'll see that when I take the square root of the number that was underneath that radical, I'm going to get plus or minus 39.5 meters per second. So, we have these equations that we've gone through a lot of effort to derive and use. However, when it comes down to it in the end, when we look at these expressions, we're going to have to use our physical intuition to decide which sign to use, positive or negative. Here I've dropped this ball, and I know that in this diagram up here, when this ball hits the ground, it's going to be traveling in the negative y direction. It's going to be going in that downward direction, so it's very messily with a mouse trying to write v sub y. I see v sub y is going to be negative, so I choose the negative sign for my final answer. Because like I said, I know the ball is falling. I know which direction it's going. So that's our first example of dropping a ball and seeing how fast it's going to be going in 40 meters per second. I'm just going to say that's fast. It's more than, I would assume it's 70 or 80 miles per hour. But it's interesting. You know how to convert meters into miles and seconds into hours. So if you wanted to, you could take that number and convert it into miles per hour. Another example, I dropped this ball from the top of the tower. I probably want to know, how long is it going to take that thing to reach the ground? And in that case, I have these three equations of motion. I choose to use the first one here. Notice when I started out this problem, I didn't know how fast that ball was going when it hit the ground, but I solved for this v sub y in the last example. So I know what that is. I know v sub naught sub y is 0. I know the value of g. The only variable in there that I don't know at this point is t. So I plug in v sub naught sub y equals 0. I just drop the thing. I just let it go without any initial velocity. I know that when it lands, hits the ground, it's going to be going minus 39.5 meters per second. I know g. I isolate t. So I take this expression. Notice v sub naught sub y is 0, so that goes away, and I end up with the total time is equal to v sub y divided by minus g. And you might be a little disturbed because you know that t is going to occur sometime in the future. I want a positive value for that, but because v sub y is negative, as shown here, my negative signs are going to cancel out, and I get that ball is going to hit the ground 4.03 seconds after I drop it. Now these are a few simple examples, and we'll solve more in class, but you should start to get a feel from having seen these equations and see me apply them to these examples, how we use them to answer questions or learn things about the behavior of objects that we drop at least.